This is the last lecture associated with Newtonian gravitation. Let me give you a basic introduction to the solar system. When it comes to the solar system is basically structured in terms of density. One of the features of gravity is that when you mix objects of different densities together, invariably the densest object will always sink to the center. So then therefore, the center of the solar system is the densest portion of the solar system, specifically the core of the sun where nuclear fusion is occurring. And then in general, the trend is that as you move outwards, the density decreases. As you move outwards from the sun, the temperature goes down as well. So when you get past a certain point in the solar system, eventually you get a number of different objects that are largely made of ice. So then therefore, if you start to think of the solar system in that manner, you can then therefore divide it up into the following regions. Okay, so we have right here the sun. The core of the sun is the densest portion of the solar system. And then you have Mercury, Venus, the Earth, Mars, and the asteroid belt. Those objects are basically all made of the same things. Basically rocks, mostly silicate minerals, and metals. So this is the next densest portion of the solar system. So you've got Mercury, Venus, the Earth, Mars, and then the asteroids, like so. All of this stuff here is basically made of rocks and metals. Okay, now with respect to the asteroid belt, by the way, how much material is actually there? Not much. It's not like the dense asteroid field that you see in episode 5, The Empire Strikes Back, of the Star Wars saga. It's not like that at all. In fact, everything there is so spread out that if you collected all of the material that is there into a single object, that single object would actually be smaller than the Earth's moon. Most of the asteroid belt is basically the 4 largest asteroids and then just a scattering of everything else. The largest asteroid is Ceres, and Ceres has, I believe, a diameter of about 500 kilometers or so. Then there are 3 other asteroids that are of similar size, and then essentially just a little bit of everything else. But then when you move outwards past the asteroid belt, then it starts to get really cold in the solar system, so then therefore you could start to have large envelopes of hydrogen and helium gas gathered together for the 2 major giant planets, Jupiter and Saturn. The cores of those planets are basically, once again, rocks and metals, but it's now colder in the outer portion of the solar system, so then therefore, ultimately what gathered around those cores were these huge envelopes of hydrogen and helium gas. That hydrogen and helium gas would not be able to exist within those large envelopes in the inner portion of the solar system. So now we've got Jupiter and Saturn. And you basically have huge atmospheres, these huge envelopes of hydrogen and helium surrounding the cores of those planets. And then each of these planets has a huge retinue or family of moons. Most of those moons are basically made up of rocks and ice, some metals, but rocks and ice. It's cold now in the outer portion of the solar system, so ices can easily form. Once again, in general, the density is going down as we move in this direction. So as we move in this direction, the density decreases. And then we have, for these objects, the moons made of rocks and ices. And then after that, you get to what are sometimes referred to as the ice giants. That is Uranus and Neptune. Uranus and Neptune are both larger than the Earth, but they are both considerably smaller than Jupiter and Saturn. Like Jupiter and Saturn, they consist of these huge atmospheric envelopes of mostly hydrogen and helium surrounding the cores of those planets. However, there are very cold gases associated with those atmospheres here in the outer portion of the solar system, namely ammonia and methane. Those really cold gases give those planets their bluish-green colors. In addition to that, however, those 2 planets also have their own family of moons. These are all fascinating places, by the way, in and of their own right. Once again, those moons are mostly made up of rocks and ice. So now we've got over here Uranus and Neptune. These guys are sometimes referred to as the ice giants, and they're similar to Jupiter and Saturn, but with very cold atmospheres. And then after that, past Neptune, you basically have debris. You have the debris that is left over, mostly ices, from the formation of the solar system. Okay, the debris that is left over is broken up into two regions. There is, first of all, a disk of material extending outwards from the orbit of Neptune out to a distance of roughly 50 AU or so from the Sun. This disk of material is referred to as the Kuiper Belt. The Kuiper Belt is the source of what are called short period comets, such as, for example, the very famous Halley's Comet. The largest object in the Kuiper Belt, or at least one of the largest objects in the Kuiper Belt, is the minor planet Pluto. There is actually another object further from the Sun that is a little bit larger than Pluto called Eris. Now, some of you may be a little bit upset to consider, for example, the fact that we no longer think of Pluto as a planet. In other words, Pluto is just one of the larger objects in the Kuiper Belt. The easiest way to define what is meant by a planet, this is the modern definition of it, is as follows. When that object formed, it gravitationally cleared out everything else that was in its orbit. So, for example, as the Earth orbits the Sun, there is nothing else in the Earth's orbit except for the Earth itself. So when the Earth formed, it gravitationally gathered up or cleared out all of the material that was there in its orbit during the formation of the solar system. Jupiter, for example, did the same thing. It gravitationally cleared out everything in its orbit. Pluto has not done that. In other words, there's this huge disk of material called the Kuiper Belt, and Pluto is just a part of that material. And then if you go further out from that still, then you end up with this huge spherical halo of debris left over from the formation of the solar system that's referred to as the Oort Cloud. The Oort Cloud extends out a distance from the Sun of roughly about a half a light year or so. We know that it's there because we have seen some objects in the Oort Cloud very far from the Sun, and the Oort Cloud is also the source of what are referred to as long period comets. So the recent comet Neowise, for example, that has been in the news these last couple of months, I'm recording this video, by the way, in early September of 2020. Well, Comet Neowise is an Oort Cloud object. It originated in the Oort Cloud. Ultimately, it will return, but not for thousands of years. So Neowise is an example of a long period comet. It originated in the Oort Cloud. So this is the easiest way to think of the solar system. Break it up into a series of zones, if you will, which are more or less organized by density. Now, when it comes to measuring density, how can you get an understanding as to what an object is made of, say in the outer solar system? Well, one thing that we can do is send a space probe, for example, out to that object, and then have that object orbit that moon. Have that probe, for example, orbit a moon in the outer solar system. What we can then do is measure the orbital period of our spacecraft, and then from there we can get a rough idea as to what the moon is made of. I've turned this into an example. This is our last example in this unit on Newtonian gravitation. Let's go ahead and take a look at it. A space probe orbits a moon in the outer solar system at a very low altitude. Show that the density of the moon can be determined by just measuring the orbital period of the space probe. That is, show that the density rho is equal to 3 pi over gt squared. So what we're asked to do here is derive an expression for the density. Okay, let me go ahead and do some erasing here. Okay, now let's say we've got this moon in the outer solar system. It's like one of the moons of Jupiter or something like that, like so. And this object has a mass, m moon. Okay, and then it says that we take our space probe, have it orbit in uniform circular motion for simplicity at a very low altitude, like so. So here's our space probe of mass m. Now, because it's at a low altitude, we're going to make an approximation here. We're going to say that the radius of our orbital circle here basically is more or less the same as the radius of the moon itself. So let's refer to this distance right here as r moon, like so. And now let's just go ahead and write, for example, Kepler's third law for this situation. T squared is equal to 4 pi squared over g times the mass of the moon times then r moon cubed, like so. So now what we're going to do is measure the period of our spacecraft and then use that to get an understanding of the density of the moon itself. In order to do this, however, you need to know what density is. Remember, of course, that three-dimensional volume density is mass over volume. So the density rho, as it's called, this is the Greek letter rho, is equal to the mass of the moon divided by its volume. If we assume that the moon is spherical, and if it's large enough, it is. If we assume that the moon is spherical, recall the geometrical formula for the volume of a sphere, 4/3 pi r cubed. Like so. Notice that an r moon cubed appears here in this expression and in this expression. So let's just go ahead and combine the expressions together, ultimately arriving at an understanding of the density. So to do so, what I'm going to do here is take this stuff in parentheses and cross multiply it to the other side to get r moon cubed by itself here from this description of Kepler's third law. All right, so r moon cubed is equal to g times the mass of the moon times t squared, and then divided by 4 pi squared. Take that expression now for r moon cubed and plug it all here into the denominator for density. Let's just be careful to cancel our terms here as we go. Okay, so now the density is going to be the mass of the moon divided by 4/3 pi, and then times r moon cubed, so times this. So g times the mass of the moon times t squared divided by 4 pi squared. And notice that some stuff begins to cancel out. So this 4 here cancels out with this 4. There's a pi that cancels here and here. And then the mass of the moon cancels here and here, like so. And now let's move some terms around. Right here is a 3 pi. Take the 3 pi and move it up to the numerator, like so. And then all that remains now in the denominator is gt squared, like so, which is what we were asked to derive. So here's a practical application now of this expression. This is an expression that is used by NASA to make a basic quick measurement. Let's say that you're orbiting a moon in the outer solar system. When you do, it's basically made of rocks and ice, so it's not all that dense. So if the density is low, this then means that the orbital period of our space probe is going to be large. It takes a long time to go around that moon because the moon's density is low. If you make a comparison, however, with, say, a space probe in orbit around Mercury, Mercury is a pretty dense object. It's close to the center of the solar system. So because Mercury is dense, this then means that the orbital period of the spacecraft will be short. It only takes a small amount of time to go around that very dense object. So by measuring the orbital period associated with your spacecraft, you can then get a rough idea of the mean density or average density of the object, which then gives you a rough idea of what the object is made of. Okay, that concludes this unit on Newtonian gravitation.